Okay, we want to look at evaluating more limits. And for this section, we're looking at functions that agree at all but one point. And the example we have here is the limit of x cubed minus 1 divided by x minus 1. And we looked at one similar to this before, but notice now we're looking at the limit as x approaches 1. And if we try to use direct substitution, what do we end up with? Well, we're going to get 1 minus 1. We're going to get 0 over 0. And when we get 0 divided by 0, this here is what we call the indeterminate form. And when we get this indeterminate form, we must rewrite the problem. In other words, from this alone, we're not able to determine the limit from this indeterminate form. And that's going to occur when you get 0 divided by 0. And what this really means is we can somehow rewrite the problem and cancel out what's causing this 0 divided by 0. And more importantly, we want to cancel out what's causing the 0 on the denominator. And for this example, we can actually factor. And x cubed minus 1, we looked at something similar to this before. This is a difference of cubes. And if you don't remember, go back and look at your formula how to factor. This is going to factor to x minus 1 times x squared plus x plus 1. Okay, again, this is just a factor of the difference of cubes. And hopefully you can tell what's going to happen here is the x minus 1s will cancel out, and now we're left with simply x squared plus x plus 1. Now, are we able to use direct substitution? Well, from here, we can use direct substitution, and we're going to end up with 1 squared plus 1 plus 1. So we end up with an answer of 3. So that is our limit. Now, what does this mean up here when I made this statement before? We're looking at a function that agrees at all but one point. Well, if we look at the original function, x cubed minus 1 over x minus 1, if we were to look at the graph of that particular function, the graph's going to look something like this, where here you're going to have an open circle at x equals 1. And that's because here, this is f of x equals x cubed minus 1 over x minus 1. If we look at the limit as we approach 1, as we get closer here, we know that this is undefined because we have division by 0. But if we look at as we get closer to this value, our limit here is approaching 3 at this particular point. Now, what we did above is we said, what happens if we factor and cancel out? Well, if we factor and cancel out the denominator, then that leaves us with the graph of a function that looks just like this. Notice what happened to this open circle. That open circle now is filled in because we're looking at the graph, we'll call it g of x, of this x squared plus x plus 1. So if you notice between these two functions, they're exactly the same function except for this one point here that's undefined for this one, but over here we fill it in. So our function now is defined at 1, so we can simply use direct substitution to give us the answer of 3. Okay, so that's what we talk about when we say we're looking at finding a function that agrees at all but one point. We're going to basically do some type of rewriting. In this case, we factored and cancel out to eliminate this part that is undefined. And once we do that, that allows us to use this particular direct substitution. All right, let's try another example. Again, if you'd like, you could try to pause and see if you could work this out on your own. We have the limit of 2x over x squared plus 4x. And if we try to use direct substitution, once again, we're going to end up with 0 over 0 if we plug 0 in for x. Okay, so again, we end up with this indeterminate form. So it looks like we should be able to factor as one of our techniques. And this one, we can actually factor a x out of the bottom. And then we notice the x on top, the x on the bottom cancels. So we're left with 2 over x plus 4. And now we can use our direct substitution. If we plug 0 in, we're going to get 2 over 0 plus 4, which would be equal to 2/4, or simply 1/2. Okay, so hopefully you're seeing here that if you get this indeterminate form of 0 over 0, once again, we can try to factor and cancel out what's causing the 0 in the denominator, and then we can use our direct substitution. All right, here we have a little bit different problem. We have the square root of x plus 1 minus 2 divided by x minus 3 as x approaches 3. And clearly, what happens if we plug 3 in? Well, we're going to plug 3 in for x. We would get 4. The square root of 4 is 2. 2 minus 2 would be 0. And 3 minus 3, we get 0 on the bottom. So that means we could try to factor, but if we look at this, there's not really anything we can factor. But what could we do? Well, another option here is we can multiply by the conjugate. And to do that, we're going to multiply the numerator and denominator by the square root of x plus 1 plus 2. Okay, so this is kind of like rationalizing the numerator. And if we do that here, we're going to end up with, in the numerator, we're going to get the square roots are going to cancel out, so you're left with x plus 1. And keep in mind, when you multiply here and here, one's positive, 2 square root of x plus 1, and this one's a negative 2 square root of x plus 1. So that middle term, they're going to cancel each other out. So then all we have left is negative 2 times 2, which is a negative 4. And if you notice on the bottom, I'm actually not going to multiply this out. I'm going to leave this in factored form. And if we combine our like terms on the top, x plus 1 minus 4, we get x minus 3 over x minus 3 square root of x plus 1 plus 2. And clearly now, what did we gain by multiplying by this conjugate? We end up with the x minus 3's canceling out. So now, are we able to use direct substitution? Well, if we take our 3 and plug it in now, we're going to get 1 over the square root of 3 plus 1 plus 2. And if we do that, we're going to end up with the square root of 4, which is 2, and then 2 plus 2, so we end up with an answer of 1/4 as our limit. All right, next we have two special trigonometric limits. And the first one here that we see is on the left. We have the limit of sine x over x as x approaches 0. Anytime you have this form, this is going to be equal to 1. And if you have a textbook, or you can go online and look, this is demonstrated through a theorem, and it talks about something called the squeeze theorem. But here, if you just memorize this limit of sine x over x as x approaches 0, that limit's always going to be 1. And the second one is if you have the limit of 1 minus cosine x over x, and this is as x approaches 0, your limit is going to be 0. So let's look at an example. If we have the tangent x over x, and we want to find the limit as x is approaching 0, once again, if we try direct substitution, we get that indeterminate form. Well, now, is there any way that we could rewrite this maybe to fit one of these special trig limits? Well, if you recall, what is our tangent function? Well, the tangent function, remember, we can think of this tangent function as sine over cosine. Okay, so if we have sine x over cosine x, then if we rewrite this, we could think of this, since this is multiplication, we could rewrite it as sine x over x, because what we're looking at here is we have this sine x over x times 1 over the cosine of x. And by doing that, we know that if we take the limit of sine x over x, we know that this limit from our sine x over x, we know that's going to be equal to 1. Okay, so we don't have to worry about anything there. And if we look at 1 over cosine, if we were to use direct substitution, we would end up with 1 over the cosine of 0, and we would end up with 1 times 1 over cosine of 0, that's going to be 1, so therefore your limit is 1. So for sine x over x, we know the limit as x goes to 0 is 1, and then for 1 over cosine x, we can simply use direct substitution to find our limit to equal to 1, and then 1 times 1 is 1. All right, one more example here. If we look at the limit of sine of 4x divided by x as x approaches 0. Well, once again, we have direct substitution gives you 0 over 0. We try the direct substitution, we get the indeterminate form. Now, if we try to fit our special trig above, we said that was the limit as x approaches 0 of sine x over x. We said that would be equal to 1. Well, notice here that when we say the limit of sine x, that means that this sine of x and this x on the bottom, they have to match up. Well, over here we have a 4x on top. So somehow we need to rewrite this so that the 4x and then this on the bottom matches. Well, we know that there's an x here. Well, to handle this, we could actually simply put a 4 here. Now, if we do that, what are we doing? we're multiplying the bottom by 4, and really we could think of, to cancel that out, we could put a 4 on top. So what have we really done here? We've multiplied by 4 over 4. Well, if you multiply by 4 over 4, that is 1. So if we're multiplying by 1, we have not changed the problem. But what have we done though? We have made sine of 4x over 4x. And if we have all of this, sine of 4x over 4x, the limit there as x goes to 0, we know the answer is 1. Well, of course, we still have this limit of 4 as x goes to 0, so we would still have the 4. Okay, and again, that would be like looking at that constant function we looked at before. The limit of 4 as x goes to 0, that turns out to be 4, and then 4 times 1 is 4.